Good morning, class. Today is November the 11th, and so this is the video for November the 12th. And as I went over in um, the chat session yesterday, I'm going to spend a few minutes covering the final project file. It is a single Excel file. This is the only thing that you are to turn in. And at the very highest level, of course you can't read anything right now, I'm going to zoom in. As I said yesterday, the number boxes, the boxes with numbers, okay, you will enter there new numbers, and in the yellow text boxes, you will enter explanations for those numbers. Now the explanations are not meant to be long, of course. As you can see, it's an Excel file. The cells do wrap text and stuff like that. So you can enter 2 or 3 paragraphs, but you're to be brief. You're to have a very concise explanation for the numbers that you chose, and hopefully you'll enjoy doing this. Now, so at the very highest level, and you can't read this, but I'll just walk through this is divided up into sectors: residential, commercial, industrial, transportation, electricity, and total fuel use. All right, so let's zoom in on something here. So let me zoom in a little bit more. Okay, so for example, let's go down here. Oops, it's hard to get this to work right. Let's go down here and let's look at the gigawatts used to generate electricity. And so you may decide that in the year 2050 that this is going to be 300. Okay, for whatever reason you make that decision. You don't explain that there. You explain the total natural gas. You can see basically. Let me go back. So the file calculates everything right. So when I change that, okay, watch this cell over here. That when I change that to 300 gigawatts, it automatically bumps up my quads of natural gas to around 49. And so, however, you change everything with natural gas. For example, you can put natural gas in transportation and things like that. You will explain this number in the end. Now, these are supposed to be 2050. Sorry about that. I forgot to change that in the file. Okay, and let's look at something else. Let's go back to transportation here, and let's say that you decide that. Well, let's first look down here at total petroleum. So this is in red because I'm going to constrain you that this number, the total amount of petroleum that's used, which is the sum of all the other fields where it's used, can't exceed 25. That we're going to make that constraint. All right, so where do you take it away from? Well, clearly you have to take it away from over here. And as explained yesterday, this field is the equivalent petroleum quads, and so it's corrected over here by the difference in efficiencies of the internal combustion engine and the electric motor. And so let's say you decide this is going to be 10. All right. Now remember, this means that 10 over this, right, or about 1/3 or so of transportation is electric. But we went over that cars are only 60% of electric. So a number 10 here would mean that you're assuming that 50% of our cars are going to be electric. I'll continue to explain that in the end. I want you to start playing with the file now and get an idea of the mechanics of it mainly. So let's say I put 10 there, all right, and you can see down here then that number has been reduced, basically by an amount of 10. Let me make sure that happened right. So if I go back 2.08, all right, see that's 42.89. So if I put 10 there, And you can watch this go down over here. Well, no, that doesn't, that's the total equivalent, okay. Where that shows up in the transportation is over here, petroleum. But then you go down, the important thing is you go down and you see that by moving that number to 10, I have dropped this number from what it was before, which is 42. So put that back to 10. And now see, it went down by 10. So you want to get that number down to 25. Now, when you look at transportation, by putting that to 10, it calculates, you know, this ratio here that we talked about based on the efficiencies of the internal combustion and electric motors. And so it automatically calculates that now you need 102 more gigawatts of electricity to run those cars. And so when you go down to the electric section here, all right, then this number has gone up, and so even though we bumped up natural gas a lot, we still have to, this number has to equal that number, meaning you have to supply enough electricity to meet all your demands. And now one thing you can, you know, if you're familiar with your Excel, you can see all the fields here where everything is calculated, and in fact, this is updated here. Because as I had said earlier in the course, I've decided that, okay, down here, there's a box for biomass. Now, that's the sum of all its uses. And what I decided is that if you think we're going to be bio in the year 2050, meaning this number is something like, you know, 25 quads or something like that, all right, because farming takes natural gas, you can see that I have an added amount of natural gas required now, equal to that number minus 6.86. That's just a rough thing. Oops. And also in electricity, you can see that I added a number here based on that biomass. Meaning, if the number exceeds some value, like around 7, okay, and this is just sort of rough. I think I meant to put 8.6 there, but basically, it means you can't get away with just making biomass without adding to your consumption of electricity and natural gas anymore. All right, now going to these base values. Now, for example, in the residential commercial, it says electricity is going to be 374. We'll discuss that and where that number comes from in the final class. It basically comes from a projection of how much electrical consumption is going to grow between now and the year 2050, which I have said is 17%. All right, and the same thing here in the industrial sector, the same thing in the total fuel for industrial, and the same thing here in the transportation. Meaning I'm assuming everything is going up by 17%, and I'll explain where I came up with that number in the final project. So you are not to change these numbers in the white boxes. Do not do that. I will get very angry if you do that, because everything fits together nicely. You will enter numbers in the other boxes. You know, for example, if you think, you know, we're going to have a lot of natural gas vehicles, you can put 10 there, all right? And you can see that got rid of a lot of my petroleum here. And so, you know, basically I've met, I should have, you know, exceeded my target of petroleum reduction. Now, let's go to, you know, I apologize having to swim around in this file, but it's just because, okay, and you see, look, by adding that 10 quads of natural gas and petroleum, I'm now below my target value of 25 quads. So what I want you to do is play with the file. 2 rules: don't change any numbers in the white boxes, only in the yellow boxes. And where is it? Okay. In electric, All right, these two numbers must equal each other, and petroleum can't be above 25. So that's all I'm going to talk about this today, and we'll we'll go over it more, and do play with it so you can ask me questions between now and December 10th, so that, you know, after December 10th, when and if you want to work on it now, if you think you understand it well, and you can start putting in explanations, you know, like nuclear, okay, right now it's 92, okay, gigawatts. Let's say you want to put in 300 there, 300. All right, you know, I mean, you can do that, and you can start to, you know, there are certain sort of key boxes here. I mean, one is nuclear, right? It's like, well, how much, you know, how much of our electricity is going to come from nuclear power plants? You can start working on that explanation, you know, now. So you can start working on the project now, but do play with it a little bit so you understand the mechanics, and so you can ask me any questions you might have on it. All right, so that's all I was going to do on the final project file today, and now let's start the normal lecture. So I'm going to turn off the projector. Actually, before I turn off the projector, why don't I go ahead and use it to quickly discuss some of the material. Okay, so we've covered. Actually, let's go to the syllabus. And so where we are in the syllabus is here, meaning we just covered heat to work, and well, actually, and we covered the gasoline engine, and now these two sort of fit together because there's another form of heat to work engine that is used primarily in electric power plants, which is the steam turbine, and that sort of leads us into our discussion then of, okay, and this is just like the homework problem on the generator. There's heat to work, that's the engine, and then there's work to electricity, and that's the generator part of that problem. And so let's first talk about the steam turbine here. Oops, I passed it. Did I pass it? There we go. Okay, here's a picture of one. So a steam turbine is kind of like a windmill. It's just with a sort of a strangely complicated version of blades. I mean, so basically, you can think of this as kind of a big windmill, except you're not blowing wind at it. You're blowing, you know, high pressure, high temperature steam, and you know, this is sort of schematically how it works, is that you have steam coming in to hit the blades here, and basically the reason why you have a set of blades like this is that you're sort of capturing different energy distributions in the steam with these sets of blades. And so it's different than a windmill. A windmill only has one set of geometry blades, whereas a steam turbine has you know, several sets, as you see here, in order to most efficiently capture all the kinetic energy in that steam blowing at it. And then the steam goes down there. And so you know, that this is a heat to work engine. You're converting heat into steam, which, you know, you can think of more as kinetic energy, but, you know, same sort of thing. You have used heat to make this steam. So you can think of the heat back here, some boiler, having produced work in the form of moving steam, that then that work is translated into a secondary work, which is the movement of the shaft, and then over here you have the actual electrical generator. So it's just like that homework problem, whereas you replace the little lawnmower engine with this thing, and then over here you have the generator. If you're interested, the steam turbine does approximately obey the Carnot system equation, and so here's room temperature in Kelvin. A typical temperature for the steam might be 1100 Kelvin, and this results in a steam efficiency that steam turbine efficiency of where is it? Well, it's around 35%. You can look off the main chart for the okay, here, yeah. So you calculate backwards about 40%, and as in the homework problem, 90% of that is the actual generator. Now, people are working on making more efficient steam turbines, and so more efficient electric power plants. There's some discussion there. What I've put in the final project, if you notice, is 35%. All right, so now, so I am going to turn the projector off in a little bit, but let's just, before I do that, look at the next section here. And the next section is sort of at a very high level, titled, okay, we did conversion of heat to work, and now, you know, just like the homework problem, we're converting work to electricity. And so we're going to learn how that is done. Now, that's at a high level. There are the things we need to learn here. And just sort of for fun, I'll relate to you a little experience I had a long time ago, because my son is now 26. In his first grade class, for some reason, I forget why, the teacher thought I was some kind of scientist, and so asked me to come in and do a class demonstration. And so, thinking of what to do, I said, well, let's play with magnets. And so I had a few projects with magnets. And one of them was where I bought one of those little electrical generators, hand-turned generators that you can buy at like a craft shop or something like that, and used it to, through the wires, generate electricity and power a little fan. So I had an arrangement of a little hand-turned generator and a little fan. And so what I explained to the class is this, that how electricity works is that a moving magnet can make electricity. That's the generator part, and that's what you'll learn here. And electricity can make a magnet move, and that's the motor part, the fan part. And, you know, really that's mostly what you have to know. Okay, now there's other things you have to know, and I'll turn off the projector in a bit, but this is kind of the set of things here. And you can see that, okay, electrical generation is part of it, but part of it is also circuit theory, because there's certain things we have to understand about electric power. Now, I realize a lot of you are electrical engineers in this course, and so this will be a review for some of you, in some cases a needed review. And I am going to start at the beginning, and the beginning is, is this. Charge, current, voltage, electric and magnetic fields, and forces. And so that's what we're going to cover today. Now, you may ask, why are we doing RLC, resistor, capacitors, and inductors, and circuit analysis? That's because you have to understand the principles of electric power, which we'll get into. And you need to, for two reasons. One, you need to understand how power actually works, particularly with regard to AC. And number two, you need to understand a little thing called power factor. And so we have to go over circuit analysis so you understand that. So let's turn off the projector now and start working at the board. That goes off. Turn on the lights. I just lost focus, of course. I'll get that back. There we go. Okay, I'm not going to touch it now. Okay, so let's start working at the board here. And so, as I said, let's start at the beginning. And so, this is, you can call this basic electrical engineering. And I won't even write the engineering because we'll just write basic electrical. Meaning, we're going to go through it from soup to nuts, starting with the beginning principles. And the beginning principles start several hundred years ago with the discovery of charge. And I think a nice way to talk about all this is to go through sort of historically how things happened. And how things started was there was a guy named Coulomb, and he discovered that they sort of knew about charges, and he discovered that if he had a charge Q1, let me write it this way. Charge Q2, okay, and they were of the same polarity, and they understood that he determined that those two charges produce a force on each other, and that force is proportional to 1 over r squared, where r is the distance between them. Okay, and I just want to follow along in the notes so I make sure I use the same notation as I already put down. And he didn't come up with the proportionality constant, so to speak, but later, and actually at the same time that the MKS unit system was made up, it was determined that proportionality constant was 1 over 4 pi something called epsilon, which is the permittivity, times 1 over r squared. And don't worry about this proportionality constant too much. All right. And additionally here, the product of the two charges, 1 and 2. Okay. And so that was very much a leap of understanding of electrical phenomena. That there was this relationship between charges and force. And now, the next step was the introduction of the electric field. Okay, and that was a very important concept, because what was determined was that, okay, if I don't have a second charge there, okay, in order to understand how everything works, people realized that at that position, you still had something, and that something was the electric field. Now I realize capital E I tend to use for energy and electric field. You're just going to have to keep in context. I could write it as a vector. I just don't want, we don't have to get confused about that at this point. I'll go ahead and put a vector there so that we know that it's not energy. So the second big leap was, okay, the realization that there's something called an electric field, and that electric field was equal to this charge and so the force I can write up here is the force on Q2 is the electric field times Q2. Force is charge times electric field. Okay, and so now we start to understand this is our beginning of understanding of how to deal with charges and electric fields, which of course you'll realize are related to voltage, and we'll get to that in a little while, and forces and things like that. And I'm going to, we've covered that energy is force times distance. We don't need to do that so much here. We can continue on in the interest of time. And, we know that voltage, V, now again, we use proliferation of variables. Here, V is voltage. Is equal to electric field times distance. Now, I'm going to put a wavy line there. And to do it properly, you write that it's the integral of electric field times distance. Now, why do we have to do that? Okay, let's draw a 12-volt battery or 9-volt battery, and let's put two terminals here. All right, this is plus, this is minus, and what's going to happen is that there's going to be an electric field generated, and what I'm going to try and do here is like make this one bigger, this one a little bit bigger, and that one smaller. And the point of writing this integral, and this is from like A to B, and so what it is telling me is that, and there's a minus sign. Don't worry about minus signs too much. What it is telling me is that if I perform this integral, whichever path I take, I come up with 9 volts. Okay, and so it's very important that we write. We understand voltage is electric field times distance, but we have to write it as this integral because we don't know what distance we're going over, okay, whether we're going over this distance or that distance or that distance. So, so this sort of is a complete picture of the description of charges and electric fields and resulting voltages that occur. Now, we've already determined that power is current times voltage, and this is basically electrostatics. Q, E, V. And there's more you have to know, but we'll get to that in a second. All right, now, the next thing is magnetostatics. Okay, which is current and magnetic field. All right, now what is a magnetic field? Okay, a magnetic field is related to the electric field, but it's something that only results when you have moving charges. So electric fields occur when I have any charge, whether it's stationary or moving, whereas a magnetic field, B, can only occur if I have a moving charge or a current. And again, I'm going to skip a few things here, in the interest of time, but let's go directly to current. So, history again. And here, the guy's name is Ampere. So just like Coulomb did this experiment with charges, Ampere did this experiment with current carrying wires. Okay, so he took two wires. So wire 1 and wire 2. And he set up currents in them, I1 and I2. Now, we're only showing, some part of the wires here. And obviously to set this current, it has to go over here to some current supply or something like that, and this one too. And so you can imagine what I've done here is I have two circuits with two wires having two different currents. And I've just sort of taken the circuit and brought together these pairs close to each other for a length, a certain length. And I've separated them by a distance d. And what he found is that they also have a force on them. And that force, F, okay, make them equal. Now one thing to note here is that magnetic forces due to currents are kind of working in the opposite way of in terms of their sign. If you have two wires carrying current in the same direction, the force is attractive. Whereas for charges, if you have two like charges, the force is repellent. Okay, and what Ampere did was he found that the force is proportional to I1, I2, now over d, over the distance, not the distance squared. Actually, if you're a fan of physics, you can actually come up with symmetry arguments why for electrostatic forces it has to be r squared, whereas for magnetic forces it has to go as length. Anyway, the proportionality constant that was then found later when people developed the MKS unit of systems is something called the permeability, mu, over 2 pi. All right. And the other thing you need here is the length over which they're parallel. And so you have mu over 2 pi, I1, I2 over dl. Now I'm going to put a little wavy line there because, okay, it's not exactly that always, because you have to perform an integration, but it roughly corresponds with what we see for. So this is magnetic, and this is electric. All right. Now, in the same manner that was determined with electric forces, what was determined is that if you have a single wire carrying a current I1, over here there is a magnetic field, B, pointing down. And so the force, the magnetic force then, analogously with the electric force, and that magnetic, I ran a room here. That magnetic field. All right, now I'm trying to draw three-dimensionally in the board here, and you have to think that the wire is going in and out of the page, and so that results in a magnetic field here. And that magnetic field is equal to mu I1 over 2 pi d. And so the force of magnetics is equal to B times I2L. And now we can generalize that by sort of plotting this in the, so taking this, and now if you're an engineer, you know, when you draw something like that, that's like the back of an arrow. So if this is I1, then the magnetic field makes a circle. I can't draw a circle. Try again. Okay, so all right, and that magnetic field. So here I try to draw it into the plane, so to speak. But if I look along the wire here, sticking in and out of the board, the magnetic field makes a circle around it, and that magnetic field is mu I1 over 2 pi d. Now, you know, you're basically learning electrical physics very rapidly here, and we're now going to sort of generalize these two phenomena. And how we're going to generalize it is I'm going to come over here, erase my battery here, and I'm going to draw my charge Q1. Now what did I learn? I learned that Q1 has an electric field over here. Now, I drew it rightly as pointing away from the charge Q1. Now, what someone realized, a person named Gauss, is that if I draw a sphere, an imaginary sphere, around that charge, all right, the electric field is going to be the same on the surface of that sphere because it's purely given by r, the distance. And so for a sphere, r is the same for all points in the sphere. Now, what Mr. Gauss did was he realized that we can generalize this knowledge by writing the following equation. We can write that the integral of E, now I'm going to write a vector calculus equation. I know that gives students problems, but let's just decompose it and go from there. If I write the integral of E dot, let me see, what did I use? S. Meaning, okay, you might have taken some math. If you haven't, I'll just say in words what it is. What that means is taking, okay, the integral of the electric field dotted with ds, and I'll draw sort of a more arbitrary version in a little bit. And I take that integral, that integral is equal to Q1 over epsilon. Now, I know that's true here, okay, because this, what is this integral? Well, for the sphere, this is equal to E times 4 pi r squared. Okay, and you can see that if I then put that 4 pi r squared over here, I get Coulomb's law. All right, so this is called Gauss's law. And you know, you may be wondering, why are we learning this? We have to know it because we have to use it to calculate capacitance. All right, and I said we had to know capacitance because we had to know power. So I mean, you can, you know, I mean, off to the side here, right? Understanding electric power, okay? We have to know, of course, voltage and current. And we have to know RLC, resistors, inductors, capacitors. And so in order to know that, we have to know Gauss's law. All right. And so because we're going to use it to calculate capacitance. So generally, if you have, if you've taken the physics class, if you have QA and QB and QC, and you draw some sort of arbitrary surface around it, that ds always points along, normal to that surface, and you take this interval, that's going to be equal to the sum of these charges contained within the surface. All right, and so we're going to use that to calculate the capacitance of a parallel plate capacitor in a little bit. Now the same thing over here with Ampere's law, and we're going to use that to calculate magnetic fields due to an inductor. So, this, I got to know what's called Ampere's law. And Ampere's law says that the integral of B dot dl along any curve, not just a circle, is equal to mu times the current contained inside of it. So if I have several currents here, and I just realized I should have had my clamp meter. Next time I'll have my clamp meter from energy audits. That if I take any collection of wires in here, it doesn't have to be one, it can be more than one. They do have to be the same phase. And I draw any surface around it, actually I have a clamp, then the integral of the magnetic field, sometimes people put this little thing here, meaning that it's a closed interval. Don't worry about that too much, okay? That it's equal to the permeability times the current enclosed inside that curve. And it's the same thing as for the sphere here. For a circle, right, that's B 2 pi, I used D. No, I used R here. All right, that turned into R, sorry. D was the distance. No, am I using R or D? Let me see in the notes. I may have switched. Okay, we'll use D. All right. If this is D, right? We already found from the basic observation of magnetic fields, forces and fields. If I do this interval, B times 2 pi d, which is the circumference of a circle, is equal to mu I1. So in both of these cases, both Gauss's law and Ampere's law, we are generalizing an example that we already know the answer for, right? We know that if I have a single wire and I integrate around a circle, B times the circumference of that circle, I get mu times the current enclosed inside. And Ampere's law generalizes that. Okay, so that if I draw a curve around any set of wires, all right, I know that the magnetic field integrated along that curve is equal to the permeability times the current enclosed inside. All right, and same thing for Gauss's law here, a charge in a sphere. And I'm going to use these because I have to understand electric power, besides current and voltage, I have to understand resistors, inductors, and capacitors To understand inductors, I have to understand Ampere's law, and to understand capacitors, I have to understand Gauss's law. Now, before we leave, we'll do Ampere's law in the next. So here I do actually have, I don't have my clamp meter, but I have a clamp sensor. And so this guy, if you look here carefully, is what's called a current transformer sensor. It's used to measure the current in a wire. It can only work for AC, but and so you can see that basically you unclamp that, and then you put your wire in there. This is for a pretty big wire carrying a lot of current, and then you close it up, and there's a coil here, and so that basically acts to, it's a transformer, we'll learn about that, via the changing electric field, or changing magnetic field, it produces a voltage at the end of this wire, which you can then plug into a meter, and so you can measure how much current is going through that opening there. And that follows directly from Ampere's law, because Ampere's law is saying, okay, this isn't a circle anymore, okay, it doesn't need to be, okay, it doesn't need to be because, all right, as long as the wire is enclosed in that circle, in that curve, that closed curve, I know that I can measure the integral of the magnetic field essentially, and I know that's, you know, proportional to how much current is going through the clamp. All right, so we'll get to inductors next time, and before we do, we'll do capacitors first. Now resistors we've kind of covered in the course, and so you know the notes explain that this section of the notes is designed for a 1-credit course embedded inside of energy systems, which I used to get more students for, and so I would have to be a little bit more formal here because these students would be coming in having not seen, you know, electric powers, current times voltage, and things like that. But you know, you guys already know that, so we can skip a few things. We have to cover the capacitor. So where was I going? Oh, so as far as resistors go, you know how resistors work, and there'll be homework problem for you to, you know, complete your understanding of them. But let me first illustrate, because it's easier to see with electric fields how to use Gauss's law, particularly for a parallel plate capacitor. So a capacitor well, let's first write down capacitance. Okay, capacitance. Capacitance is a definition. All right, that's a first important thing to realize about capacitance. Capacitance is defined as the capacity to hold charge at a certain voltage. Meaning, if I have two conductors, okay, 1 and 2, and I put Q and Q minus on them, right, and there's a voltage between them, the capacitance is equal to Q over V, by definition. So for example, if I were somehow able to levitate myself above the floor here, and I had somehow acquired charge in my body, and the floor had acquired the opposite charge, the voltage between myself and the floor could be determined by calculating the capacity of the system of me and floor, and dividing that into that charge that I put on my body. So capacitance, it's what it sounds like. It's the capacity to hold charge at a certain voltage of some system of two conductors, basically. Actually, they don't have to be conductors, but it's easier to think about them that way. So the simplest capacitor, right, is a parallel plate capacitor. Let's try and draw this. So you have two plates, and we have, actually, sorry here. I should have written, yeah, this is V plus minus. Let's do it that way. So there's a voltage between the plates of V, and there's a charge Q and Q minus on them. And I would like to know what the capacitance is, because C, right, is equal to Q over V by definition. So the first thing to realize is that if I have a voltage between the plates, it results in an electric field E equal to, and I'm not going to look up what units. I think I used H here for the separation between the plates. V over H. All right, now how do I know that? Because I know voltage is field times distance. So that means that electric field is voltage over distance. And because it's a uniform electric field, okay, I don't have to worry about all the integrals and stuff. I can just write it down. It's just voltage divided by distance. That's all it is. Now, if you get really sophisticated, you have to realize that at the edge of the capacitor, the electric field might do something a little bit funny, but we ignore that complication and neglect it here. Now, so we know the electric field, and so we know the voltage, and so we know the electric field, V over H. And because we know the electric field, think about it, we can figure out the charge. All right, because we know that this formula always works. So if I draw an imaginary mathematical surface here, all right, now first of all, I have to realize that E equals 0 outside the plates. Okay, now why is that true? Okay, well, you can reason it out. If I made my imaginary mathematical surface on both sides here, right, by symmetry, it has to be 0, because if it weren't 0, that would mean that there's some net charge between them. But I said Q is equal to Q minus. All right, so by definition then, E has to be 0. And I put the other end of my pillbox here, and so the integral of that, I'll write it over here, the integral of E dot ds. Now remember, it's dot, so there's nothing along the sides here, because that dot means that, remember, this is ds, it points away from the surface. So the only contribution is there. And since the electric field is uniform, that's just equal to E times A. And I can extend that over the entire capacitor of area A. And that is equal to the charge enclosed, which is Q, times divided by epsilon. All right, and now I have, okay, and now I can write that in terms of V, because I can plug in for E. So I have that V over H, A, is equal to Q over epsilon. And so rearranging, right, I have that Q over V is equal to epsilon A over H, and that's C. So I've used Gauss's law to determine that if I go in the laboratory and I try and build a capacitor by putting two parallel plates together, all right, that the capacitance of that capacitor is given by the permittivity. Now, we haven't talked about permittivity too much, we'll just table that for a little bit. I do have a homework problem that I'll probably assign this weekend. Well, let's talk about permittivity. Okay, so permittivity is equal to something called a relative permittivity times epsilon naught. And this is the permittivity of free space, which is 8.854 times 10 to minus 12. Now, if you work out, you can work out the units as farads per meter. Now, where does this number come from? That's like the speed of light. Basically, it's a universal constant that we've learned about the universe. And epsilon here depends on the material. So what that means is that if I just put air there, right, I get a capacitance based on epsilon naught. And whereas, for example, if I put what's called a dielectric, now certain capacitors have oil, where we can have an epsilon of hundreds. All right, so usually you put some material in there to increase the permittivity and increase the overall capacitance. But anyway, this is the answer, and you'll need that for the homework this weekend to be able to perform some calculations. And we'll stop there for today. Next time I'll use Ampere's law to come up, with properties of an inductor in the same manner that I use Gauss's law today to come up with the capacitance of a parallel plate capacitor.